We're looking at moles, and what you have to remember here with moles is that if we say we have 1 mole of a substance, and it could be 1 mole of any substance, that would contain 6.02 times 10 to the 23 atoms, particles, ions, or any other chemical entity. Now this number here, okay, that 6.02 times 10 to the 23 is referred to as the Avogadro's constant, and you may have heard of this before. So Avogadro's constant, and you've heard of that before. Really, really important this number is. Now, it's a bit like the baker's dozen. A dozen is 12. Yeah, so 1 mole means I've got 6.02 times 10 to the 23 atoms, particles, or ions. So if I've got 2 moles of any substance, that means that will contain 12.04 times 10 to the 23 atoms, particles, or ions. So we're just twice or double the actual number, the Avogadro's constant. And then what we've got, if we say have half a mole of any substance, that would contain 3.01 times 10 to the 23 atoms, particles, or ions. So you can see we've halved that Avogadro's number. Okay, so that is where the moles is. Now we need to relate moles in our day-to-day chemistry. And I want to refer back to our periodic table. So if we look at our periodic table, I'll bring the periodic table up here. Okay, so the essence of when we're using Avogadro's and moles and when doing any mole calculations. So what's important here is that you look at the elements, okay, the symbols, and you have the mass numbers. So yeah, I'm going to give an example here. I'll just focus here, say, on the beryllium. So Be, and Be has got a mass number, a relative atomic mass of 9, and it's got an atomic number of 4. What's really important is that number there, the number 9, because that is the mass number, and the mass number is really important. And if I show you here on my next sheet, and we can actually lift off this periodic table. If I actually say here I've got Be, and that's a 9 and 4, and what we've ended up with here now is this. We've got that 9, that's the mass number. If I weighed out on a balance exactly 9 grams of beryllium, okay, 9 grams of beryllium is 1 mole. That means that if I had 9 grams of beryllium I weighed out on a balance, I would have 1 mole. So I would know exactly how many atoms are in 9 grams of beryllium. I would have exactly 6.02 times 10 to the 23 atoms. Okay, carbon. Okay, if we look at carbon, carbon is this, carbon is 12 and 6 there. Again, that 12, that's the mass number. And if I exactly weighed out 12 grams of carbon is 1 mole. And we know that that's 1 mole, so I'd know exactly how many atoms are there. I would have 6.02 times 10 to the 23 atoms. Okay? So the mass number is equal to the mass of 1 mole of a substance. That means that if you weigh out according to the mass numbers of any of the elements in the periodic table, that is the mass to get 1 mole of a substance. So therefore you would know exactly how many atoms you'd have there. You'd have 6.02 times 10 to the 23 atoms. Okay. Now, in reality, when we're doing chemistry, we never use these large masses. We only use small amounts or small masses of substances. And so we've got this really, really important equation you would have come across. Okay, and that equation you would have come across would have been this. It would be moles is equal to the mass over the MR. Now the MR could be the molecular mass, the whole molecule. You might have 2 or 3 elements in the compound, okay, and you've got to work out the molecular mass of that. Or you'd have a relative atomic mass. So it doesn't matter what you've got there, but then you've got the mass which is there, which you'd obviously weigh out, and you can work out the number of moles. So you have seen this before. Now, at A level, we don't like using triangles to rearrange. You need to know how to rearrange. So please do learn how to rearrange without using triangles. So you would have to use this. Now, I'm going to give you an example here. So I'll keep it very simple. So just say I had, instead of weighing out, so we'll stick with carbon, 12 and 6. So instead of weighing out 12 grams of carbon, we're not going to weigh out 12 grams of carbon, but instead I say weighed out, say, 6 grams of carbon. Okay? So weighed out 6 grams of carbon, how many moles would I have? So what you do there is you'd say the moles is equal to, you've got 6 grams, which is the mass, 6 grams at the top, and the atomic mass is 12. So it's 6 over 12. So I'd have 0.5 moles there. So that would mean that if I've got 0.5 moles there, I'd have 3.01 times 10 to the 23 atoms. Okay? And that's how you manipulate this particular equation to work out the number of moles from, you won't have the exact mass of 1 mole, you'll have different masses, so you can work the moles out accordingly. Let's give you one more example. And this time, the example is going to be this. I'm going to give you a compound, and we've got CaCO3, calcium carbonate, and I am going to weigh out 10 grams of calcium carbonate. So how many moles have I got there? So what you first will do, you've got calcium carbonate, you work out or you look at your periodic table, you find the relative atomic masses. So you've got calcium, which is 40, you've got carbon, which is 12, you've got oxygen, which is 16, but you've got 3 of those oxygens, so you times that by 3, you add them all together and you end up with 100. Okay, so that's what the MR is. So the MR is 100. So we can work out what the moles is. The moles is the mass over the MR, and we know we've weighed out 10 grams of that calcium carbonate, or CaCO3. Divide that by 100. So what we've ended up now with is 0.1 moles. So that's how many moles I've got. Okay.